This is going to be second fundamental theorem of calculus. We're going to skip the first part of this and we're going to do a chain rule version only. And the chain rule version really includes the first part as well. So we're going to work this out the long way one time and then we'll do the shortcut the rest of the time. And then after I work this out the long way, then I'll talk about what it says in that box and that formula that represents the second fundamental theorem of calculus. So first we're going to start off with the antiderivative. The antiderivative of cosine is going to be sine. And that's sine t integrating with respect to t. And then after we do the antiderivative, then we will plug in the upper limit, we will plug in the lower limit, we would subtract upper limit minus lower limit. So this is the sine of x squared minus the sine of pi over 6. The sine of pi over 6 is a half. And then after we do the antiderivative here, then we can apply that derivative operator. The derivative of sine is cosine, leaving the inside alone, times the derivative of that inside, which is 2x, and then the derivative of that constant half is 0. So then we end up with this 2x cosine of x squared. What I want to notice about this is what I have is the integrand, which is cosine, with the upper limit plugged in to the integrand, and then times the derivative of the upper limit. And so that's what it says in the box. Well, we want to take the derivative of an integral, where the upper limit is a function of x, plug the upper limit into the integrand times the derivative of the upper limit. That's also what this formula says. When I want to take the derivative of an integral where the upper limit is a function of x, plug the upper limit into the integrand, that's what gives me f of g of x times the derivative of the upper limit. The upper limit's g of x, so the derivative of the upper limit is g prime. So we're going to use the second fundamental theorem then and apply it to these problems. For all of these problems, maybe not all of them, but for definitely A, B, and D, we don't know how to integrate those functions, and we're not going to learn how to integrate those functions. What we want to do is recognize this as a second fundamental theorem type problem. Taking the derivative of an integral where the upper limit is a function of x, then I'm going to plug the upper limit into the integrand times the derivative of the upper limit. The upper limit in this case is just 1. Same for the next function. I'm going to plug the upper limit into the integrand. I'm taking the derivative of an integral where the upper limit is a function of x. I'm going to plug the upper limit into the integrand times the derivative of the upper limit. Taking the derivative of an integral where the upper limit is a function of x, I'm going to plug the upper limit into the integrand times the derivative of the upper limit. Same for the last one. Taking the derivative of an integral where the upper limit is a function of x, I'm going to plug the upper limit into the integrand times the derivative of the upper limit. The derivative of sine is cosine. And then this one we could rewrite as with that exponent next to the trig function. I do want to say one thing about what's up here. I do want the upper limit to be the function of x, so if the upper limit's not the function of x, then we're going to flip the limits, and when we flip the limits, then that means we have to multiply by a negative. So negative the integral from a to x for f of t dt. And then we can bring that negative out in front. Negative the derivative of the integral, where the upper limit is a function of x. Then that's going to give us the negative of the upper limit plugged into the integrand times the derivative of the upper limit, which in this case the derivative of the upper limit is just 1. These are all example problems. So what I would say about the example problems is work the example problems A through F and then check your answer. We'll work the example problems at the bottom of the page together. This says on what intervals is f decreasing. F is this function that's defined by an integral. F decreasing is where f prime would be negative. And so I need to find f prime, which means I'm taking the derivative of integral where the upper limit's a function of x. I'm going to plug the upper limit into the integrand times the derivative of the upper limit, which the derivative of this upper limit is just 1. And then if I want to find out where this derivative is positive or negative, then I'll set that equal to 0. We'll find our critical values, and undefined, but this derivative is a polynomial, so it's never undefined. Factor x and x, 3 and 2, minus and plus. X equals negative 3, x equals positive 3, x equals negative 2. Sign chart, plugging into f prime is going to tell us what's happening to f. Two values, negative 2 and 3. The sign chart is going to be positive, negative, positive. And we're looking for decreasing, so we're looking for that negative interval. F is decreasing for negative 2 to 3 because f prime is negative. Write the equation of line tangent. So for tangent line, point slope. The x-coordinate of the point is negative 1. To find the y, we're going to plug negative 1 in for x. Y equals 3 minus the integral from negative 1 to negative 1, e to the negative t cubed dt. When the upper limit and the lower limit are the same for an integral, then that integral has a value of 0, so this becomes 3 minus 0, which the y value then is 3. The slope of the tangent is going to come from the derivative, so dy dx. The derivative of that constant 3 is 0. Then we have minus the derivative of an integral where the upper limit is a function of x. We're going to plug the upper limit into the integrand times the derivative of the upper limit, which is just 1. And then when we evaluate dy dx at x equals negative 1, it gives us negative e to the negative of negative 1 cubed. This is going to be negative e to the positive 1. That's our slope. And once we have the point in the slope, then we can write the equation of the tangent line. Y equals the slope times x minus the x, where we're subtracting the negative, plus the y. And then the last one, we're finding the values of each of these statements. So first finding f prime of x. So f prime of x, taking the derivative of an integral where the upper limit's a function of x. I'm going to plug the upper limit into the integrand. So replacing t squared plus 8, replacing t with x squared, plugging the upper limit into the integrand, times the derivative of the upper limit. The derivative of x squared is 2x. And then a little simplifying, this is 2x, x to the fourth, plus 8. That's f prime of x. F prime at 1, plugging in 1 is 2 square root. 1 to the fourth is 1, plus 8 makes 9. So 2 times the square root of 9, which is 6. Part C is the derivative of f prime, the second derivative. So then, to do the second derivative here, we're going to need to do product rule. The first function times the derivative of the second function, 2x being the first function, that square root of x to the fourth plus 8 being the second function. The derivative of the square root is 1 over 2 square roots, leaving the inside alone, times the derivative of the inside, which is 4x cubed. And then we need to do the second, x to the fourth plus 8, times the derivative of the first, which is 2. And then if we do just a little simplifying here, this 2 and this 2 divide out, x and x cubed, they're going to make x to the fourth, so 4x to the fourth over the square root of x to the fourth plus 8 plus 2 square roots of x to the fourth plus 8. And we could probably even do some more simplifying by getting a common denominator, but how far we go just depends on whether this is a multiple choice or a free response problem. F double prime of 1, I'm going to plug 1 in for all the x's. It's going to give me 4 over the square root of 9 plus 2 times the square root of 9. So then 4 thirds plus 6. 6 as a fraction with the denominator of 3 is 18 thirds, so this gives me 22 over